How's it going, friends? Welcome back to the logs and welcome back to voice logs. This should be episode 7, if I am not mistaken. And now we're just hanging out. We're hanging out late on a Friday evening, and we're studying some biochemistry. So I've just been going through and reviewing. I haven't actually. Well, let's reset the brain right there. I have an exam on Tuesday in biochemistry, so I've been reviewing, naturally. And I was going through my lectures, and what I like to do when I review now is just to listen to the lecture. They have them all recorded now, so you can just pop them up, put them on like a couple times speed, and go through them fairly quickly. So I just kind of have my notes open as I go, and I review what I'm doing. But for lecture 3, they inadvertently did not record the lecture. I guess there was a IT issue across campus, and the lecture was not recorded. So I thought, wouldn't it be fun if I went through the lecture with you guys? And instead of the professor talking to me, I talk to you. I don't know how much fun that will be, but let's see. Maybe it will be fun. Maybe I'll have some fun. And if not, if nothing else, it'll be a review. It'll be a review for me. Maybe it'll be a review for you. Whatever it is, it's going to be fun. We're going to have fun. So, as I said, we are reviewing biochemistry. It's not really intense biochemistry, so we're not really focused too much on the structures. It's more medical biochemistry. So we take biochemical things, like right now we're talking about hemoglobin in this third lecture, and we just kind of apply it to clinical diagnoses. So we try to take a different spin on it and use what we know in biochemistry to find the causes of disease, the underlying causes of disease. So in this lecture, we had kind of built up in lectures 1 and 2, we've built up the idea of hemoglobin. What is hemoglobin, and what is its role in the body? Excuse me. So in this third lecture, we are talking about hemoglobinopathies and thalassemias. Hemoglobinopathies are actually genetic disorders, and thalassemias are also genetic disorders. So, okay, what is hemoglobin? Hemoglobin is in your red blood cells, the blood cells that flow through your veins to bring oxygen to your tissues. Red blood cells carry, they're basically bags of hemoglobin, this substance that attracts oxygen. So when you take a deep breath, like that hemoglobin flowing through the veins and through the arteries in your lungs will catch that oxygen and then deliver it, once it's returned to the blood and then pumped, will deliver it to your tissues. And then once it's there, it will just literally drop it off of the tissues that need it. So that's what hemoglobin does. And in this third lecture, we're talking about genetic disorders that can cause genetic defects in hemoglobin, just in the structure of it. So, as we've said, we can have a hemoglobinopathy. As it says here, hemoglobinopathies, it's a group of genetic disorders, and they generally, because they are genetic disorders, so the instructions on how to create hemoglobin are disordered. They're wrong. So you produce a structurally abnormal hemoglobin. And on the other hand, so you have that hemoglobin is just built wrong. And then on the other hand, you have a thalassemia. So a thalassemia results from the synthesis of inefficient quantities of hemoglobin. So it's also a genetic disease, but it's a different kind where you just can't produce enough of some of the pieces of hemoglobin to make enough hemoglobin to fit in a red blood cell so it can carry a good amount, like a solid amount of hemoglobin, so it can carry a solid amount of oxygen to your tissues. So let's see. We reviewed that. We got that down. Normally, hemoglobin, a molecule of hemoglobin, is made up of four kind of groups, four proteins. You have 2 alpha and 2 beta proteins. Doesn't really matter which one's like alpha 1, alpha 2, beta 1, beta 2. They're the same thing. And they just kind of, that's where like the 4, it can carry up to 4 oxygens. That's where each of the oxygens would go. So you just kind of think of hemoglobin as one team with 4 team members, and each team member can carry an oxygen. And a hemoglobinopathy would be an error in that team. So, you guys didn't meet up at the right time, that team, or the team was not functioning well together, and it disbanded. So you have a structurally abnormal team, or hemoglobin. Thalassemia, on the other hand, is just an inefficient quantity of normal hemoglobin because you couldn't make enough teams. In a regular sort of team, maybe you have 800 people, and you could make a solid 200 teams. But now in a thalassemia, say you only had 400 people, so you could only make half the teams that you could before. So you just can't carry enough oxygen to those tissues. There aren't enough people. There are not enough team members. So that's kind of how you can think about it. And that's kind of how I can think about it now because I just made up that little thing. So let's go. So the terminal objective, let's see. The objective for this lecture, lecture 3, is to just understand what genetic diseases and genetic alterations could do to the synthesis and the structure of hemoglobin. So kind of the stuff we just reviewed in that intro. Sorry for the little pauses here. I'm just kind of reviewing the information and then I'm going to tell it to you. So first up, we're talking about the organization of hemoglobin. So we've got hemoglobin and... Okay, so here. We've got alpha and beta genes. As I've said, those are 2 gene families, just general. And the alpha genes are located on your 16th chromosome, or chromosome 16. And your beta genes are located on chromosome 11. Okay? Not too crazy there. So that's where they're going to be manufactured. If you know anything, do you know about, it's like you're going to respond to me. I'm saying, do you guys know about DNA replication and transcription of the DNA? So when you're transcribing this DNA, it'll transcribe this whole thing in your chromosome, and then it'll kind of cut it down to an mRNA, and that mRNA will go into the cell, and then it'll be transformed into a protein, basically, or transcribed. It provides the directions for that protein. So the directions for the alpha genes, or the alpha part of the hemoglobin, are on chromosome 16, and the directions for the beta gene, or the beta part of the hemoglobin, are on chromosome 11. That's just where they're kind of hanging out. And yeah, so you build a couple of those, you build a couple of these, and you make a hemoglobin. So easy, so easy. Let's see. Oh, so that's what it's talking about next. I'm one step ahead of these notes, guys. Okay, steps in globin chain synthesis. Yeah, so expression of the globin genes. Here's the thing. With red blood cells do not have a nucleus. and they do not have mitochondria, as many of you may know as the the powerhouse of the cell. Please don't when. Okay. I took I'm a biology major, and I took AP Bio in high school. Took a lot of bio in undergrad, and I'm still living the bio life with anatomy and things like that. A mitochondria. It's called the powerhouse. I'm doing air quotes right now. The powerhouse of the cell, but it's not really the powerhouse of the cell. It's not producing like electricity. It's not a power plant. It's not a coal factory or whatever. It's the site of DNA. Oh, hold up. I'm reading DNA and I'm telling you DNA, but it's not. Doesn't really have much to do with DNA. It has its own DNA, which is interesting because not a lot of organelles or little things within the cell, not a lot of those have their own DNA. Really, it's only the nucleus, which is like the hub of all the DNA in your cell that has DNA. Mitochondria are the site. Mitochondria is plural and mitochondrion is singular. So mitochondria are the site of ATP synthesis within the cell. So say that, next time you're talking about mitochondria with your friends, just say, hey guys, mitochondria is not really the powerhouse of the cell. It's the site of ATP synthesis. And ATP is a molecule with a high energy phosphate group that can phosphorylate and therefore cause changes within the cells, like within enzymes, for example, and activate, deactivate enzymes. Pardon, I'm just wiping down my glasses. I just kind of hit my finger against it and then all the oil and stuff. Do you guys hate when that happens? Any of you with glasses out there, have you just like, when you just have your glasses on all day and then you kind of take them off and you just randomly and then you just see all the stuff that's on it? You're like, how am I seeing through all this? Like what the hell? Anyway, so we went over mitochondria. Yeah, so you have no excuse for getting mitochondria wrong anymore. It's not the powerhouse of the cell, site of ATP synthesis. Okay. What do we talk about? Okay, we're talking about red blood cells, right? So red blood cells, they don't have a nuclei, and they don't have mitochondria. So what does that mean? It means in mitochondria use oxygen to create ATP. The problem with having mitochondria in red blood cells is that when you're using oxygen, you're not delivering oxygen, right? You want red blood cells, the whole goal there is to deliver oxygen to the tissues so that your cells can breathe and make their own energy and stuff like that. And, just survive. And by removing those, you're removing the mitochondria, so you're not using oxygen. You're removing the nucleus, so you can't build new stuff because the directions for building all the new stuff are gone because the DNA is gone. And so that's all gone. And then, you're just kind of saving space for more hemoglobin. So that's why I mentioned like the bag of hemoglobin earlier. That's what it literally is. There's just a lot of hemoglobin. So, and they're flat. So it's nice flat little pancakes. They kind of look like donuts, but it's like you punched in the two sides because, there's no donut hole. It's just kind of like flattened. It's called a biconcave disc. So that's interesting. It's biconcave, so it's two concave sides. So you have a lot of surface area, to pick up. So you have all that hemoglobin at the surface, so you can pick up a lot of oxygen. And you have no stuff, like no organelles inside to take up space or to use the oxygen. So that's always fun. but the precursors to the red blood cell, so the cells that come before it, as they're maturing to become red blood cells, they have all that stuff. They have a nucleus and they have mitochondria, and then they lose it before they're sent out into the blood to do their job. So the hemoglobin, the globin genes are, remember, we talked the 14 members. So when those are starting to be made, they're being made in the nucleus and in the cell of those early red blood cells. And they're being transcribed. They're being copied down. The directions are being copied down from the DNA, and they're being made. And then they're released into the cytoplasm, or outside of the nucleus. And that's where they're being physically made. And then you get hemoglobin. And slowly you build, and you have so much hemoglobin, and then you release your nucleus, you get rid of your mitochondria, and you have a red blood cell. So this is when it starts to get a little interesting. The thing is with hemoglobin, there are multiple types of hemoglobin. So you have hemoglobin A, which is adult hemoglobin, which is, it's like the main hemoglobin. About 90% of the hemoglobin in your body is hemoglobin A. And it has 2 of the alpha and 2 of the beta, just like we were saying, those 4 team members. And that's like the main thing. That's like the main guy. When you think of hemoglobin, it's probably hemoglobin A. If you've ever, just thought of hemoglobin randomly. So it's hemoglobin A, and that's like the main thing in your body. That's the main thing that's used in your body to transport oxygen. But that's not the only hemoglobin, because hemoglobin is a family of molecules. Pardon me, I'm just going to grab a quick drink here. A little parched. I don't know how those lecturers do it. Just talking for like 50 minutes, just straight about this stuff. It does kind of hit you after a little bit. And you got to be, correct in your information. It's as if they know the next slide, but, they've been doing it for a while, but still. So in the family of hemoglobins, you've got hemoglobin F, and hemoglobin F is fetal hemoglobin. So that's the type of hemoglobin that you have when you're a fetus, when you're growing in your mama's belly, as they say. So hemoglobin F is another type of hemoglobin. And the interesting thing about hemoglobin F is that it's starting to be produced around the 5th week of gestation. And that's when you have, like, in the beginning, you have these embryonic hemoglobins, nothing, not really interesting. The 5th week, you start to get the fetal hemoglobin, and then it's really about the 8th month that you start to build your hemoglobin A, which is your adult hemoglobin. But what's interesting about hemoglobin F, or fetal hemoglobin, has a higher affinity for oxygen than hemoglobin A does. It's due to this other molecule that kind of plays a role, but just simply, hemoglobin F has a higher affinity, so it wants oxygen more than hemoglobin A does. So you're saying, I don't get it. What does that mean? Well, hemoglobin F is flowing through. So just imagine this. You've got a mother, and she's got her baby, her fetus, and hemoglobin through the bloodstream of the fetus and through the placenta, and hemoglobin A, sorry, not through the placenta, through the fetus, right? Hemoglobin A is coming from the maternal blood supply to feed the fetus. And one thing that the fetus needs, a nutrient, it needs nutrients, but it also needs oxygen so it can supply its tissues and grow. But the thing is, when you have hemoglobin A and it's oxygenated, so those 4 team members are carrying oxygen, it doesn't really want to let go of its oxygen until it reaches the tissues. Hemoglobin F, wanting the oxygen more, will go and take it from hemoglobin A. It's like you've got one team saying hemoglobin A, it's just like normal people, and hemoglobin A, super buff people, like muscly dudes, and they just go beat up hemoglobin A and take their oxygen. Or, well, they don't. Okay, let's see. How can we think about this? Maybe they're buff, scary dudes, and hemoglobin A is like, okay, take it. You know, I don't want to get in a fight. I don't want to have any trouble here. So just take the oxygen. So it's like that. As the two are kind of flowing by each other, where the maternal blood supply meets the fetal blood supply. So yeah, that's the interesting thing about fetal hemoglobin. And so that's why a majority of the fetal blood supply is fetal hemoglobin. It's about the 8th month, as I've said, that the adult hemoglobin or hemoglobin A starts to replace that fetal hemoglobin. And that's why you need fetal hemoglobin, so the fetus can get oxygen, so it can grow and it can feed its tissues and nourish itself. In the adult, fetal hemoglobin usually doesn't account for very much, maybe less than 2% of all hemoglobin that's in the body. So it doesn't really play much of a factor after birth. But it's important when you're in the placenta. What else? So we're not done with the family of hemoglobins. We've got hemoglobin A2. Hemoglobin A2 is another sort of minor sort of hemoglobin that you have as an adult. It appears after birth, and it doesn't really take up more than 2% of the total hemoglobin. There's not really much to say about that. It's just hemoglobin A2, just another type. Hemoglobin A1C is an interesting hemoglobin because it's kind of like a transformation to hemoglobin A. So we've said hemoglobin A are those 4 team members, right? 2 alpha team members, 2 beta team members. What happens with hemoglobin A1C is that glucose or sugar is added to hemoglobin A. This process is known as glycation. So hemoglobin A plus glucose create hemoglobin A1C. For some of you, maybe a lot of you, A1C sounds very familiar because increased concentrations of A1C are found in people with diabetes because there's more glucose in the blood. Therefore, there's more glucose to contact this hemoglobin A, just regular hemoglobin, and you create with that hemoglobin A, which I just read it off the notes as HbA because Hb is how you kind of shorten up hemoglobin. I don't know why not Hg. Oh, Hg is mercury, so that's why I caught myself. Hemoglobin A and glucose make. So again, when you have more glucose in the blood, your hemoglobin is coming more and more into contact with glucose, hemoglobin A1C, and that's why hemoglobin A1C is used as an indication of the level of blood glucose. And it's over a 120-day period because that's the lifespan of an average red blood cell, 120 days. So that's an interesting hemoglobin in the family, and it's an interesting use for hemoglobin so that you can see you have a concrete test that you can do for patients with diabetes to check their glucose concentration in their blood to keep everybody healthy, right? So that's good. That's in the family of hemoglobins. It's not really it is a type of hemoglobin, I guess you can say. It's created from hemoglobin A and glucose. So yeah, that's the family of hemoglobin. You've got your just regular hemoglobin A. You just the top guy, 90% of them, hemoglobin A. Then you've got hemoglobin F, as we've said, the fetal hemoglobin. Hemoglobin A2, which is kind of like the odd guy out. And hemoglobin A1C, which is pretty useful. So now we're moving to hemoglobinopathies. Hemoglobinopathies, as I've said, result from an error in the directions for creating hemoglobin. So here's one disease. Hemoglobin S, hemoglobinopathy, so it's an error in the directions or error in the DNA. And hemoglobin S, or more often called by its name, sickle cell anemia, is actually the most common type of hemoglobinopathy, and it's the most common type of red blood cell sickling disease. So there's an error here in chromosome 11. Right, let me just check. Yes. On chromosome 11, beta part of hemoglobin, so the beta T member is being manufactured. That beta part, there's an error in one little part of the directions. It's called the point mutation. So one little letter in this long list of letters is off. So, and you get, instead of just a generic run-of-the-mill beta globin little protein, instead of a beta T member, you receive a beta S T member. And we'll talk about that in a little bit. So yeah. So a lot of sickle cell is one of the most common blood disorders that is inherited in the U.S. It's autosomal recessive. So that means you have to inherit one part of the gene from each parent. And so infants with this disease don't really show many symptoms because they're still carrying that hemoglobin F. And then as it's being replaced by hemoglobin S, the erroneous one, it starts to show its true colors, I guess. And it starts to show the symptoms, basically, of hemoglobin S. It's a very, very painful disease. The red blood cells only live for about 20 days, or less than 20 days, when compared to 120 days for regular hemoglobin A hemoglobin. So there's high turnover for the cells, and in many cases there are just episodes of pain, or called crises, and it's from chronic anemia, hemolytic anemia, because there are just so many cells that are being destroyed at once, and you're lowering the amount of oxygen you can carry. It can block your blood cells. It can block the blood vessels because they're kind of like weirdly shaped, so they can kind of catch and block the blood vessels, so blocking blood reaching the tissues, so your tissues can die. You have an increased susceptibility to infection because the blood flow isn't as good, so a lot of the infection-fighting cells can't really get to the places that they need to be. It's a very, very horrible disease. And researchers are actively trying to fix it, to find a way to fix it. So now I hope I've done a justice to the introduction here, and let's continue. We're talking about that point mutation, as I said. So it's like one letter change in the whole stream of letters that make up this direction for this hemoglobin. So I said that beta globin, which is the beta team member, remember, of the 4, because there are 4 team members, 2 are alpha, 2 are beta, and together they make hemoglobin. So those 2 beta hemoglobins are wrong. They have an error. So one amino acid, which is a part of a protein, it's kind of the thing that makes up a protein. So a bunch of amino acids make up a protein. And in this case, in that position where there's the error, remember I said you're changing the letter, you change from a, hold on. Okay. I just want to catch my thoughts so I don't make a mistake. So you're changing at that position. So I said in the long chain where there are a bunch of letters, in that one place where the letter's changing, you're changing and causing a less amino acid to be in that place. So that means that you have a less negative amino acid in that place where before you had a more negative one. Okay? I think we're good there. What that also means is that you go from a less, or you go from a more hydrophilic or water-loving cell to a more hydrophobic water-hating cell or water-scared cell. So what does that mean? In a normal red blood cell, you have this negative amino acid, and water is polar. I think maybe you study that in general biology. But water is a polar molecule, so it has a negative side and it has a positive side. And it uses that. That's one of the main things why water is so incredible and why water is just everywhere and it makes us up and it has all these cool properties is because of that polarity. It's got a negative side and it's got a positive side. So water can kind of shovel together, touching one positive side to one negative, another negative to another positive. So that's why water can pool together. And that's why water can, like, have you ever had like a pool of water, say, like, or you spilled some water on your table, right? And then you just kind of take a napkin or a paper towel and you just touch the corner of that paper towel to the water. And then you'll see slowly the water will just go up and up and up and up and up and up the paper towel. And you're like, okay. You just kind of you don't really think about it. But if you did think about it and just like took a second, like, wait, how is this water climbing against gravity? Because it was just on the table lying flat. Well, that's a cool property of water. It's called cohesion and adhesion. So water can stick together and stick to things. And it's because it's a negative molecule. So, a negative molecule, it's a polar molecule. So since it's got these negative and positive sides, it can do that. It can stick to itself and stick to other things and basically climb. And that's why trees can grow. The other reason, because their roots have these little, I think it's the xylem. The xylem, the thing that collects water. Correct me if I'm wrong, but I think it's the xylem, and it's like this little tube that goes to the roots, and then it could just transport water up and up and up and up the tree. And it needs the capability of cohesion, adhesion. So it has this capability of cohesion and adhesion, and it could do that. It can climb up a tree. So back to our discussion of red blood cells. So those sickle cells, since they are less hydrophilic, so that means they're less water loving because they're more non-polar, or they're less negative. They have less charge, right? So, and water likes charge because, okay, let me use another example to explain this more fully. Have you ever just put like a tub of water, or better yet, talk about a salad, right? right? And you put some oil in the salad and you have some water pool at the bottom, that oil and water will not mix because oil is a nonpolar substance and water is a polar one. So oil will just kind of stick to the top of it. That's the same thing that's happening here. Hemoglobin S is less negative than hemoglobin A. So what hemoglobin S is doing is that it doesn't like the water, so it's kind of like cowering or changing shape to kind of put all its water-liking, water-loving sides on the outside and all its water-hating sides on the inside. And because it has extra water-hating sides, it forms that sickle shape. That's very characteristic of sickle cell anemia. Hemoglobin A has that negative amino acid, so it doesn't have that issue. So it forms a nice round shape and that biconcave disc that we're talking about. So that's the interesting thing about sickle cell anemia. And the other thing with sickle cell anemia is that not all cells are sickle shaped. A lot of the time when you're studying this disease, the pictures show a bunch of sickle shaped the cells that are abnormally shaped. It's many of them, but they're not all sickle shaped. It's just a few that are of this. It's just hold on. Let me catch my words here. It's just many of them that are sickle shaped among the very, very many normally shaped ones. So that's the main thing. So you have these cells, they're misshapen, they stiffen and they're distorting, they're distorted, and that means they could block the flow of blood in those, especially those very narrow capillaries that we have all over our body. When it's just they have a room for sometimes just one cell to pass by at a time, and you could just block that and then cause that crisis that we were talking about from oxygen deprivation, because the rest of the blood, it's kind of like when somebody gets into an accident and then they block the whole street. So that first cell is just kind of blocking. Or when there's construction is a big thing, especially around Chicago. Chicago, there's two seasons, winter and construction. So construction blocks the whole road and you can't move. So that's a big thing. So sickle cells can block a capillary, and then the rest of the blood cells cannot move to go to their destination. It's not a good thing. And so that anoxia can result because there's just less oxygen that could reach those tissues. Oxygen deprivation. So yeah, that's a big thing. That's the main idea behind sickle cell disease, or the hemoglobinopathy that is labeled as hemoglobin S. The one thing, though, that it comes why you would think you're just thinking why has it been kept in the population, hemoglobin S? Because you think that unhelpful traits would be removed slowly. Well, there is an advantage to people that carry the recessive trait. So they have one normal, so they have normal red blood cells, but they also carry the trait for unnormal or irregular, those sickle cells. And it's because the sickle cell red blood cells only live about 20 days. And that means that people with this trait or with this gene have an advantage against malaria, because the main parasite that causes malaria spends part of its life cycle within the red blood cell. So if you get bit by a mosquito with this kind of malaria, this parasite, what the thing will do is go to the red blood cell and then just kind of hang out there. and it's in a normal, say, take a normal 120-day red blood cell. The parasite will live and kind of grow in that red blood cell and eventually be released to the rest of the body. But with those red blood cells that can only live 20 days, the red blood cell just dies before the parasite can even finish. So it's kind of an advantage there. So those people that have sickle cell traits have an advantage there with malaria because they can't get malaria, or much less susceptible to that severe malaria. So that's why it's kind of been kept in the population and not removed because of its, symptoms. It's horrible symptoms. Yeah, so that is hemoglobin S disease. I'm sorry for my very choppy sort of delivery of that. I'm actually kind of trying to review as I'm talking to you, so I don't want to get the information right, especially if I'm going to put it out. So it takes a little bit. But yeah, so that's hemoglobin S disease. And again, with this review, you can kind of tell it doesn't really sound too much like biochemistry. It sounds a little bit more like maybe bio, because there's not too much chemistry going on. But we're kind of talking about like the DNA synthesis and things like that, and there is applied chemistry in terms of the polarity and things like that. Kind of like what we just talked about, hydrophobicity, hydrophilicity, things like that. And so it's an interesting take on what biochemistry is, and especially in the medical setting, and how it applies to that medical setting. So you kind of learn the background behind a lot of diseases, especially in the clinical setting where you're dealing just with the disease and you're not really thinking about all the background that can help you more fully understand and more better treat the disease. Because that's the main thing why we're taking this class, why biochemistry is a class taken at medical school. It's to more fully understand the processes of the body, the body chemistry, the life chemistry or biochemistry. So it's an interesting class, and it's interesting to learn more and more about, well, for one, how they're teaching the class and how they're kind of more readily applying the topics that we're talking about, and instead of using structures and mechanisms to study chemistry, the structure of the molecules and the change in the structure of the molecule due to an enzyme acting on it or things like that. It's interesting to see that it's more thought-based biochemistry and more clinical-based biochemistry, where they will give you a word problem versus just a generic like problem you would get in organic chemistry or inorganic chemistry, or even undergrad biochemistry, to kind of just say, oh, this is the end product, show me the mechanism of how we got here. And you kind of have to draw out, we're rushing out to draw all those little structures to get to the end thing. So it's an interesting take, so that's just a little insight into my review. I think we're getting into, we're about 44 minutes into the episode, so I think, we've got a little bit more to review, but I won't bore you with stuff like, we didn't review much of the thalassemias, but we kind of did at the beginning. I hope it was at least a little bit entertaining to hear. Maybe just learn a little bit more about what I'm reviewing and the hemoglobin and stuff like that. which readily applies to a lot of people. We talked about hemoglobin A1C and diabetes. It's very highly likely that you know someone with diabetes, and you just know a little bit more about the treatment plan and the way that we understand it. So it's always nice to know, because it's always nice to just know, right? It's a nice thing to be able to review and to just know things. So I hope you enjoyed the episode. I enjoyed kind of going through this stuff with you. It's nice to just kind of review and to just talk out loud and to talk to all of you about things going on. So I hope you enjoyed this, because I'd love to make more episodes of voice logs on school and stuff like that. It's the stuff that I'm doing. So, and make it more like a vlog sort of deal. Maybe take you throughout my day. So thank you guys for listening. Thank you guys for caring. And remember, always laugh, keep happy, and keep listening to the logs. And while I'm here, follow the logs everywhere on those social media platforms. Again, they're always going to be linked down below. Follow us on the Twitter. Follow us on the Facebook and the Instagram. We've also got a YouTube channel, so if you want to have a transcription of the episode, go right to the YouTube channel, click closed captioning. You have a transcription right there ready for you. So that's always available. And always that store on Teespring is always available for y'all. And go check out those awesome styles. We're thinking of some new styles that are coming out. We're still working on them. So please enjoy those, and please purchase stuff that you love. They're very comfortable. Hoodies and crew necks and tees. Get one for you, get one for your family, for a loved one, and look awesome. So thanks, guys. Keep on listening to the logs everywhere you listen to podcasts. Keep on laughing, keep on having fun, keep on being happy. And we'll see you in the next one.